A military rescue helicopter is climbing hard over the Hindu Kush Mountains in Afghanistan. The pilot is pushing everything the machine has. And then, somewhere around 13,000 feet, the helicopter simply stops climbing. Not because the engine quit. Not because anything broke. The air just ran out of the ability to hold it up. That is not a malfunction. That is physics. And once you understand what is actually happening inside those rotor blades, you will never look at a helicopter the same way again. Most people assume helicopters are stopped by their engines. Run the motor hard enough, push enough power through the shaft, and the machine goes wherever you point it. That assumption is wrong in a way that has killed pilots, stranded rescue missions, and forced military engineers to completely rethink rotorcraft design from the ground up. The real limit has nothing to do with the engine. It has everything to do with what a rotor blade is actually doing every single second it is spinning. A helicopter does not float. It does not hover by magic or momentum. It flies by violence. Each rotor blade is a wing, shaped exactly like the wing on a fixed-wing aircraft, curved on top and flatter underneath. As the blade spins, air rushes over that curved surface faster than it rushes underneath. That speed difference creates a pressure difference. Lower pressure above, higher pressure below. And that pressure difference is lift. But here is the part that changes everything. The blade is not pushing against the helicopter. It is pulling against the air. Every pound of lift that rotor generates is borrowed directly from the air molecules it passes through. The blade grips the air, bites into it, and yanks the helicopter upward. Now imagine trying to paddle a kayak in deep, dense water. Every stroke grabs a solid wall of resistance. You pull hard, the paddle bites, the boat moves. Now imagine draining half the water out and replacing it with loose, wet foam. Same paddle, same stroke, same effort from your arms. But the blade passes through something thinner, something with far less resistance, and the bite just disappears. You are working just as hard and going nowhere near as fast. That is exactly what happens to a rotor blade as a helicopter climbs. At sea level, the air pressing down over most of the continental United States weighs roughly 14.7 pounds per square inch on everything it touches. It is thick with molecules packed tightly together. A rotor blade moving through that air finds something real to grab onto. The pressure difference between the top and the bottom of the blade is significant. Lift is almost generous. At 10,000 feet, that same column of air weighs less. The molecules are spread further apart. The blade sweeps through the same arc, at the same speed, burning the same fuel, and generates measurably less lift per revolution. The helicopter is now working harder for the same result it got for free closer to the ground. At 14,000 feet, air density has dropped to roughly 60% of what it was at sea level. The rotor is not flying through air anymore. It is flying through something closer to a suggestion of air. And the helicopter is starting to lose the argument with gravity. Here is where most people's instinct completely leads them off a cliff. The natural reaction is simple. Just spin the rotor faster. More revolutions per minute means more lift generated per second. The math sounds clean and obvious. It is not that simple. And this is the detail that almost nobody tells you. Rotor blades have a hard speed limit, and it has absolutely nothing to do with the engine. The outermost tip of a helicopter rotor blade is already moving at somewhere between 400 and 500 miles per hour during normal flight at sea level. That is not a typo or an exaggeration. The tip of a blade on a Black Hawk helicopter in a standard hover is moving at nearly the speed of sound, covering an enormous arc, hundreds of times every single minute. Push the rotor speed higher, and those blade tips approach the sound barrier directly. When a rotor blade tip goes transonic, the airflow around it does not just slow down, it breaks down completely. Shockwaves form along the leading edge. Aerodynamic drag explodes to levels the rotor was never designed to handle. Vibration tears through the airframe. The rotor does not generate more lift by spinning faster. it generates less lift, while simultaneously shaking the machine to pieces. There is a hard wall, and the rotor is already frighteningly close to it during normal operations. So the pilot cannot simply spin faster. The blade shape is fixed by the manufacturer. The rotor diameter is fixed by the airframe. And the air is getting thinner with every foot of altitude gained. The helicopter is methodically running out of options. The ceiling a helicopter hits is not printed in the manual as a hard stop or a flashing warning light. It is called a service ceiling, and it is defined as the altitude at which the aircraft can no longer climb faster than 100 feet per minute. Not the altitude where it stalls and falls out of the sky. The altitude where it is essentially treading water in the air, burning every ounce of available power, just to creep upward 100 feet every 60 seconds. For most commercial and utility helicopters, that ceiling sits somewhere between 10,000 and 14,000 feet above sea level, depending heavily on temperature, total weight carried, and humidity in the surrounding air. A fully loaded medevac helicopter on a hot July afternoon in Denver, which already sits at 5,280 feet above sea level before it lifts off the pad, is starting every single flight with a measurable and serious handicap baked in before the wheels leave the ground. That is why high-altitude operations are not just a harder version of normal flying. They are a completely different engineering problem, wearing the same uniform. The United States Army and Special Operations Forces learned this lesson at tremendous cost in Afghanistan. The mountain ranges of eastern Afghanistan sit between 8,000 and 12,000 feet above sea level across vast stretches of operating territory. Forward operating bases were built at altitudes where standard Black Hawk and Chinook helicopters were already running near their operational ceilings before they absorbed a single bullet, carried a single soldier, or lifted a single pound of supplies. A Chinook helicopter operating at sea level can lift roughly 26,000 pounds of useful cargo. The same helicopter, same engine, same rotor system, operating at 10,000 feet on a summer afternoon, might lift fewer than half that number of pounds before it runs out of rotor authority to climb. The aircraft did not get weaker overnight. The air got thinner, and the rotor simply ran out of enough air molecules to bite into. The military response was not to wish for denser air or lighter soldiers. It was to engineer around the physics as aggressively as possible. High-altitude rotor systems use longer blades. A longer blade sweeps a wider disk of air with every single revolution. More disk area means more air molecules engaged per rotation, which partially compensates for the lower density at altitude. Think about the difference between cooling a room with a small handheld fan versus a large ceiling fan in the exact same space. Each blade still finds less resistance to grab at altitude, but the total sweep is so much wider that the net lift available improves meaningfully. Some high-altitude helicopters use rotor blades with entirely different airfoil profiles, cross-sections specifically shaped to generate useful lift at lower air pressures than standard blades were ever designed to handle. These blades are thinner in their construction, more aggressive in their camber, engineered specifically to wring every available pound of lift out of air molecules that are barely cooperating. Turbine engines are also modified for high-altitude operations. Standard turbine engines suffer in thin air, not because they lose raw mechanical power from the shaft, but because they physically move less air mass through the combustion chamber every second. Less air means less fuel can burn efficiently in each cycle. Engineers compensate with variable inlet guide systems and high-altitude rated compressor stages that squeeze and compress the thin available air into something the combustion chamber can actually use productively. But none of these modifications eliminate the ceiling. They raise it. A standard utility helicopter that tops out operationally at 12,000 feet might be re-engineered and certified for a service ceiling of 18,000 or even 20,000 feet with enough investment and redesign. The underlying physics does not change or bend. The engineering just pushes the wall back far enough to get the mission done. The absolute outer boundary of what helicopter physics allows was demonstrated on May 14, 2005, when a pilot named Didier Del Sol flew a small single-engine Eurocopter AS-350B3 to the summit of Mount Everest, 29,032 feet above sea level. The air density at the Everest summit is roughly 1/3 of what exists at sea level. The Rotor was working in conditions that would have shut down virtually every other production helicopter ever built and certified. Del Sol touched down on the summit and stayed for 3 minutes and 58 seconds. Not a leisurely landing, a controlled, desperate balancing act at the absolute edge of what the rotor blades could physically grip. Every additional second on that summit was another second of exposure to a system running with no margin whatsoever. Then he lifted off and came back down the mountain. That flight was not a demonstration of normal capability. It was proof of exactly where the wall sits and exactly how thin the air gets on the other side of it. Here is what every high-altitude rescue operation, every mountain medevac, and every special operations insertion into the Hindu Kush ultimately comes down to at a physical level. A helicopter is a machine that negotiates with air. At sea level, the air is generous and cooperative. There's plenty of density to work with and the negotiation is straightforward. But as altitude increases, the air becomes progressively less willing to participate. The rotor has to work harder, push closer to its tip speed limits, grab more aggressively at molecules that are increasingly far apart from one another. At some point, and that point is different for every helicopter depending on its design, its weight, the temperature that day, and the humidity in the air around it, the air simply stops cooperating entirely. The engine might still have shaft power available to give. The pilot might still have skill and instinct and training to apply. But if the air surrounding the rotor disc is not dense enough to be meaningfully grabbed by a blade moving at the edge of the sound barrier, the rotor has nothing left to pull against. And a rotor blade with nothing to pull against is just an enormously expensive piece of carbon fiber and titanium spinning hard in air that has already decided it is done helping. That is the service ceiling. Not a line printed on a performance chart by a cautious engineer in an office. A physical wall built entirely out of missing molecules, erected by altitude itself, and completely indifferent to how much the pilot needs to climb another 100 feet. Now consider what happens on the other side of this problem. If thin air defeats a helicopter by starving its rotor blades of molecules to grip, what is happening to a commercial jet engine at 40,000 feet, where the air is even thinner, even colder, and the pressure is a fraction of what exists at sea level? Why do Boeing 747s and Airbus 380s not hit the same wall and simply stop flying? The answer involves a completely different relationship between forward speed and air density, and it rewrites a significant part of what you just learned about how lift behaves when the atmosphere starts running out. That explanation is worth its own deep dive. And if this one left you